Welcome! In this session, we'll explore problem number 1380, lucky numbers in a matrix. Together, we'll understand the problem, break it down step by step, and examine a potential solution. Let's dive in and solve this interesting challenge. In this problem, you are given an MXN matrix of distinct integers. Each element in the matrix is identified by its position at the ith row and jth column. The task is to find all the lucky numbers in the matrix. A lucky number is defined as an element that is both the smallest number in its row and the largest number in its column. The output should be an array containing all such lucky numbers, and the order in which they appear in the array does not matter. The constraints specify that the matrix dimensions can range from 1 by 1 to 50 by 50, and all elements are distinct integers between 1 and 100,000. Let's look at an example to clarify the concept. Consider this 3 by 3 matrix, 3, 7, 8, 9, 11, 13, 15, 16, 17. The output for this example is 15. Here's why: the number 15 is the smallest element in its row, 15, 16, 17. This means it satisfies the first condition for being a lucky number. To check the second condition, we look at the column containing 15, which is 15, 9, 3. Since 15 is also the largest number in this column, it qualifies as a lucky number. Now, let's analyze another example. Take this 3 by 4 matrix, 1, 10, 4, 2, 9, 3, 8, 7, 15, 16, 17, 12. The output here is 12. To see why, note that 12 is the smallest element in its row, 15, 16, 17, 12. So, it satisfies the first condition. Next, we examine its column, 2, 7, 12, where 12 is the largest value. Thus, 12 meets both criteria to be a lucky number. Here's one more example to solidify the concept. Consider the smaller 2 by 2 matrix, 7, 8, 1, 2. The output is 7. That's because 7 is the minimum element in its row, 7, 8. When we check the column, 7, 1, where 7 is located, we find that it is also the maximum value in that column. Therefore, 7 qualifies as the lucky number for this matrix. To wrap up, let's review the constraints and some edge cases. The constraints ensure that the matrix has at least one row and one column but no more than 50 rows and 50 columns. Each element in the matrix is unique and falls between 1 and 100,000. For edge cases, consider a matrix with a single element, like 42. Here, the output is 42, since the only element is both the row minimum and column maximum. Another edge case is a matrix where no lucky number exists, such as 1, 2, 3, 4, which results in an empty output. This happens because no element satisfies both conditions simultaneously. Finally, let's look at one more example to understand how lucky numbers can appear in a slightly larger matrix. For the matrix 3, 6, 7, 1, 5, 8, the output is 8. In this case, 8 is the smallest number in its row, 5, 8. Checking the column 6, 1, 8, where 8 is located, we see that it is also the maximum value there. Hence, 8 is the lucky number for this matrix. To solve the problem of finding lucky numbers in a matrix, let's first consider the brute force approach. The intuition here is straightforward: a lucky number is the minimum element in its row and also the maximum in its column. To implement this, we start by iterating over every element in the matrix. For each element, we first check if it is the smallest in its row by comparing it with all other elements in the same row. If this condition is satisfied, we then check if it is the largest in its column by comparing it with all other elements in the same column. If both conditions hold, we add the element to our result. However, while this approach is simple and easy to understand, it is computationally expensive. The time complexity is O, m asterisk n asterisk, m plus n, where m is the number of rows and n is the number of columns, because we end up performing redundant checks for each element in the matrix. On the other hand, the space complexity is O, 1, as we don't use any additional data structures. While intuitive, a high computational cost makes this approach less practical for larger matrices. Now, let's explore an optimized approach that avoids the redundant computations of the brute force method. Instead of checking every element, we focus first on identifying the minimum element in each row. By storing both the value and the column index of these row minimums, we can efficiently track potential candidates for lucky numbers. Next, for each of these row minimum elements, we check if it is the maximum in its corresponding column by scanning through that column. If both conditions are satisfied, the element is added to the result. This approach is far more efficient because it eliminates the need to repeatedly compare all elements in the row and column for every matrix element. The time complexity is reduced to O(m*n), as we only traverse the matrix row-wise and column-wise once. The space complexity is O(m), as we need to store the row minimums. By reducing redundant computations, this method is both faster and simpler. Additionally, there is an alternative approach using sets, where we store the row minimums and column maximums in separate sets and find their intersection to identify lucky numbers. While this approach is also efficient, it requires additional space for the sets, making it slightly less optimal in memory-constrained scenarios. The time complexity of the set-based approach is O(m*n), as we still traverse the matrix row-wise and column-wise once. However, the space complexity increases to O(m+n), because we use sets to store both the row minimums and column maximums. This trade-off makes the set-based method efficient in terms of computation but less favorable in terms of memory usage compared to the optimized approach. After carefully evaluating the trade-offs, the optimized approach is the chosen strategy. It avoids redundant computations by focusing only on row minimums and their corresponding columns. Additionally, it is straightforward to implement and achieves lower space complexity than the alternative approach using sets. This balance of efficiency and simplicity makes it ideal for competitive programming. In contrast, the brute force approach was rejected due to its high computational cost. While the set-based alternative is competitive in terms of runtime, its additional space requirements make it less desirable in scenarios where memory usage is a concern. The key observations that guided this decision include recognizing that the problem can be broken into two independent conditions, identifying row minimums and verifying column maximums. By pre-computing row minimums and directly checking column maximums, we significantly reduce redundant checks. The pivotal insight was understanding the independence of these conditions, which allowed for a structured and efficient solution. In conclusion, the optimized approach strikes the best balance between time and space complexity, making it the most suitable solution for this problem. By focusing on row minimums and their corresponding columns, it avoids unnecessary computations while keeping the implementation simple. This approach is efficient, easy to understand, and ideal for scenarios where computational resources are limited. It not only meets the problem's requirements but also exemplifies how breaking a problem into smaller, independent conditions can lead to an elegant and effective solution. In this problem, we are tasked with finding lucky numbers in a matrix. A lucky number is defined as an element that is both the smallest value in its row and the largest value in its column. To solve this, we begin by understanding the structure of the matrix. It has m rows and n columns, and any element could potentially be a lucky number. However, to validate this, we need to ensure it meets both the row and column conditions. A straightforward way to approach this is with a brute force method. We iterate through each element and check if it is the minimum in its row and the maximum in its column. To break this down further, the first step involves identifying the minimum value in each row. We iterate through every row in the matrix, locate the smallest value within that row, and store it along with its column index in a list called row_min. This will help us track potential candidates for lucky numbers based on the row condition. Next, we focus on the columns. For each column in the matrix, we identify the maximum value. This is stored in a list called col_max, which keeps track of the largest value in each column. With the row minimums and column maximums identified, we can now check for lucky numbers. For each row, we take its minimum value from the row_min list and compare it against the maximum value of its corresponding column in the col_max list. If the row minimum matches the column maximum, then the element is a lucky number. Finally, all identified lucky numbers are collected in a result list, which we return as the output. To illustrate this, let's consider an example with a matrix 3, 7, 8, 9, 11, 13, 15, 16, 17. This will help us visualize the process step by step. Starting with the row minimums, we examine each row. In the first row, the minimum value is 3, which is located in column 1. For the second row, the minimum is 9, also in column 1. In the third row, the minimum value is 15, again in column 1. Therefore, the row underscoreman list is 3, 1, 9, 1, 15, 1. Now, moving to the column maximums, we check each column. In column 1, the maximum value is 15. In column 2, the maximum is 16. In column 3, the maximum is 17. This gives us the col_max list as 15, 16, 17. To find the lucky numbers, we compare the row minimums with the column maximums. For the first row, the minimum value of 3 does not match any column maximum. Similarly, for the second row, the minimum value of 9 does not match any column maximum. However, for the third row, the minimum value of 15 matches the maximum in column 1. Therefore, the only lucky number in this matrix is 15, and the result is 15. This approach highlights several key insights. First, by separating the problem into row-wise and column-wise operations, we eliminate unnecessary computations and streamline the process. Additionally, we can implement early termination. If the minimum value in a row is smaller than all column maximums, we can immediately skip further checks for that row. This saves computational effort. It's also important to consider edge cases. For example, in a single element matrix, the element is always a lucky number since it is both the row minimum and the column maximum. In some cases, there may be no overlaps between row minimums and column maximums, resulting in no lucky numbers. For larger matrices, efficient handling of rows and columns becomes crucial to maintain performance. Using specific data structures helps here. The input matrix remains unchanged, while row_min and col_max store the intermediate results, and a separate result list holds the lucky numbers we identify. Now, let's analyze the complexity of this algorithm. The time complexity involves 3 main operations. Finding the row minimums requires iterating through each element, which is O, m*n, where m is the number of rows and n is the number of columns. Similarly, finding the column maximums also takes O, m*n. Checking for lucky numbers is done row by row, which takes O, m. Combining these, the overall time complexity is O, m*n. For space complexity, we store the row_min list of size m and the col_max list of size n, resulting in a space complexity of O, m plus n. To optimize further, we can pre-compute the row minimums and column maximums to avoid redundant calculations. Additionally, we can skip rows entirely if their minimum values are smaller than all column maximums, which reduces unnecessary comparisons. These optimizations ensure the algorithm is efficient even for larger matrices. This implementation solves the LeetCode problem number 1380, lucky numbers in a matrix, which requires finding all numbers that are both the minimum in their respective rows and the maximum in their respective columns. The solution begins by calculating the minimum value for each row. This is achieved using a list comprehension that iterates over each row in the matrix and retrieves the minimum value of that row. The result is stored in the row_min list. Next, the code calculates the maximum value for each column. To achieve this, it uses the zip function to transpose the matrix so that columns become rows. It then computes the maximum value for each column using another list comprehension, storing the results in the col_max's list. The final step is to identify the lucky numbers. This is done by iterating over each element in the matrix using nested loops. For each element, the code checks whether the value is equal to both the corresponding row minimum, from row_mins, and the column maximum, from col_max's. If the condition is satisfied, the number is added to the lucky_numbers list. Finally, the function returns the list of lucky numbers. This approach ensures that the solution is both efficient and easy to understand. The use of comprehensions and zip simplifies the code while maintaining readability. The algorithm effectively handles edge cases, such as matrices with a single row or column, and ensures correctness for all inputs within the problem's constraints. Here, we start by defining a function called LuckyNumbers which takes a 2D integer array, or matrix, as input and returns a list of integers. The first step is to find the minimum value in each row of the matrix. To do this, we create an array called romance to store the minimum value for each row. We initialize all elements of romance with the maximum possible integer value. Then, we iterate over each row and column of the matrix. For every element in the matrix, we compare it with the current minimum value for that row. If it's smaller, we update the row's minimum value in romance. This ensures that by the end of the loop, romance contains the smallest element from each row. Next, we move on to finding the maximum value in each column. Similarly, we create an array called callmaxes and initialize all its elements to the smallest possible integer value. We then iterate over each column and row, and for every element, we check if it's greater than the current maximum for that column. If it is, we update the column's maximum value in callmaxes. By the end of this loop, callmaxes holds the largest element from each column. Now that we have the row minimums and column maximums, the next step is to identify the lucky numbers. We define a list called lucky numbers to store these special values. We then iterate through each element of the matrix using nested loops. For each element, we check if it matches both the row's minimum value and the column's maximum value. If it does, we add it to the lucky numbers list. This ensures that only numbers that satisfy both conditions are included. Finally, we return the lucky numbers list, which contains all the lucky numbers in the matrix. This approach ensures that we efficiently find the required numbers while keeping the code simple and readable. To solve the problem, we begin with a simple 3x3 matrix. The first step is to find the minimum value in each row. Looking at row 0, the minimum value among 3, 7, 8 is 3. For row 1, the minimum value in 9, 11, 13 is 9. Lastly, for row 2, the smallest value in 15, 16, 17 is 15. This gives us the row minimums as 3, 9, 15. Next, we calculate the maximum value in each column. In column 0, the maximum value among 3, 9, 15 is 15. For column 1, the maximum value in 7, 11, 16 is 16. Finally, in column 2, the largest value in 8, 13, 17 is 17. This gives us the column maximums as 15, 16, 17. Now that we have the row minimums and column maximums, the next step is to identify the lucky numbers. A lucky number is a value that is both the minimum in its row and the maximum in its column. Starting with cell 0, 0, the value 3 matches the row minimum but not the column maximum, so it is not lucky. For cell 1, 0, the value 9 is the row minimum but not the column maximum, so it's also not lucky. However, for cell 2, 0, the value 15 matches both the row minimum for row 2 and the column maximum for column 0. Therefore, 15 is a lucky number. The output for this example is 15. Moving on to a non-square matrix, we follow the same process. The first step is to find the minimum value in each row. In this new example, we start by calculating the row minimums. For row 0, the minimum value in 1, 10, 4, 2 is 1. For row 1, the smallest value in 9, 3, 8, 7 is 3. Lastly, for row 2, the minimum value in 15, 16, 17, 12 is 12. This gives us row minimums of 1, 3, 12. Next, we calculate the column maximums. In column 0, the largest value among 1, 9, 15 is 15. For column 1, the maximum value in 10, 3, 16 is 16. In column 2, the largest value in 4, 8, 17 is 17. Finally, in column 3, the maximum value among 2, 7, 12 is 12. This results in column maximums of 15, 16, 17, 12. To identify lucky numbers, we now check each cell in the matrix. Checking the cells, we start with cell 0, 0, where the value 1 matches the row minimum but not the column maximum, so it is not lucky. For cell 1, 1, the value 3 matches the row minimum but not the column maximum, so it is also not lucky. Finally, for cell 2, 3, the value 12 matches both the row minimum for row 2 and the column maximum for column 3. Therefore, 12 is a lucky number. The output for this example is 12. Let's now consider a scenario where the matrix has no lucky numbers. The process remains the same, starting with the row minimums. Here, for the given matrix, row 0 has a minimum value of 5 from 5, 6, 7. Row 1's minimum value from 8, 9, 10 is 8, and row 2's minimum value from 11, 12, 13 is 11. This gives us row minimums of 5, 8, 11. Next, we calculate the column maximums. In column 0, the maximum value among 5, 8, 11 is 11. For column 1, the largest value in 6, 9, 12 is 12, and for column 2, the maximum value in 7, 10, 13 is 13. This results in column maximums of 11, 12, 13. After checking each cell in the matrix, we find that no cell satisfies both conditions of being a row minimum and a column maximum. Hence, there are no lucky numbers in this example, and the output is an empty list. To analyze the time complexity of solving this problem, we can break it into 3 key steps. The first step is finding the minimum value in each row of the matrix. For this, we use Python's min function, which scans through each row to find the smallest value. Since the matrix has m rows and each row has n columns, the computation for one row takes n time, and doing this for all rows results in a time complexity of m*n. Next, we need to find the maximum value in each column. To do this efficiently, we transpose the matrix using zip matrix, which takes m*n time, and then calculate the maximum for each column. With n columns and each requiring m operations, this step also has a time complexity of m*n. So for these first 2 steps, both contribute m*n to the overall time complexity. The third and final step is to check for lucky numbers. Here, we iterate through all the elements of the matrix and compare each one against the corresponding row minimum and column maximum. This involves 2 nested loops, one iterating through the rows and the other through the columns. The inner comparisons require O1 time, so together, the nested loops perform m*n comparisons. This step therefore has a time complexity of m*n. When we sum the time complexities of the 3 steps m*n for the row minimums, m*n for the column maximums, and m*n for checking lucky numbers, we get a total time complexity of m*n. This confirms that the solution is linear with respect to the number of elements in the matrix. Now let's discuss the space complexity of the solution. In the first step, we store the minimum value of each row in a list called row_mints. Since there are m rows, this requires m additional space. In the second step, we store the maximum value of each column in another list called col_maxes. With n columns, this step requires n space. For the third step, we keep track of the lucky numbers in a list called lucky_numbers. In the worst-case scenario, such as in a diagonal matrix, there could be up to min lucky numbers, which requires min space. Additionally, during the transposition operation using zip matrix, a temporary view of the matrix is created in memory, which demands m*n space. This temporary storage dominates all other space usage in the solution. Taking all these factors into account, the overall space complexity of the solution is determined by the temporary transposed matrix, which requires m*n space. Comparing this optimized approach to a naive method highlights its efficiency. In the naive approach, we would iterate through every element of the matrix, and for each element, check if it is the minimum in its row and the maximum in its column. This involves n time for the row check and m time for the column check, resulting in a time complexity of m plus n, which is much worse than the optimized solution. The optimized approach achieves m*n time complexity by precomputing the row minimums and column maximums, avoiding redundant calculations. In terms of space, both approaches require m*n space due to the transposed matrix, but the optimized method is more efficient overall in managing memory. In conclusion, the proposed solution is optimal for solving the problem of finding lucky numbers in a matrix. It achieves a time complexity of m*n by efficiently breaking the problem into 3 steps and pre-computing necessary values, and its space complexity, while also m*n is dominated by the temporary transposed matrix. This balance of time and space efficiency ensures that the solution performs well even for larger matrices. Here are some common mistakes to watch out for when solving the lucky numbers in a matrix problem. One major issue is not verifying both conditions, that the number is the minimum in its row and the maximum in its column. Overlooking either condition can lead to incorrect results, so it's critical to check both explicitly. Another mistake involves inefficient nested loops for column checks. Recomputing the maximum of a column multiple times within a loop adds unnecessary computation. Instead, you can pre-compute the maximum values for all columns at the start to save time. It's also easy to confuse row indices with column indices during matrix traversal. To avoid this, use clear variable names, like row and col, and double-check your indexing. Finally, assuming the matrix is always square is another pitfall. The problem may involve rectangular matrices, so always design your solution to handle general MXN matrices rather than assuming NXN by default. Another common oversight is failing to handle edge cases. These include scenarios like empty matrices, single row or single column matrices, and matrices with duplicate values. Testing your solution against these cases ensures robustness. On the interview side, optimization is often key. While brute force might work for small inputs, interviewers expect you to optimize for larger matrices. For instance, pre-computing row minimums and column maximums can significantly reduce computational complexity. Be ready to discuss how your solution handles edge cases, like matrices with identical values in a row or column. Clear communication is also important. Articulate how you verify the two conditions step by step. Finally, be prepared to explain trade-offs. For example, if your approach reduces time complexity at the expense of increased space usage, make sure you can justify why the choice is appropriate. If you want to deepen your understanding, exploring related problems can be very helpful. For instance, LeetCode 54, Spiral Matrix, emphasizes matrix traversal techniques, which are foundational for working with 2D arrays. LeetCode 74, Search a 2D Matrix, focuses on efficiently handling 2D arrays, particularly in scenarios where they are sorted. LeetCode 766, Toeplitz Matrix, examines row-column relationships in matrices, a concept that overlaps with the logic needed for lucky numbers. Finally, LeetCode 378, KTH smallest element in a sorted matrix, explores how to work with matrices that are row or column-wise sorted. Each of these problems provides an opportunity to strengthen your matrix manipulation skills, which are directly applicable to solving the lucky numbers challenge. Now, let's look at some alternative approaches to solving the problem. One effective method involves pre-computation. Instead of checking row minimums and column maximums repeatedly during traversal, you can pre-compute these values upfront. This reduces computational redundancy and speeds up the process, though it requires additional memory for storing the pre-computed values. Another approach uses sets. You can collect all row minimums and column maximums in two separate sets, then find their intersection to determine the lucky numbers. This method is elegant and concise but may require extra space for the sets and additional operations to compute the intersection. Lastly, there's an optimized brute force method. Here, you iterate through each row, find its minimum value, and directly verify whether it meets the column maximum condition. While this approach is simpler to implement, it can still have a time complexity of O(m*n) in the worst case, making it less efficient for larger matrices. Great job! To summarize, we explored the concept of lucky numbers in a matrix and discussed an initial brute force approach. Remember to practice similar problems to strengthen your understanding. Thanks for tuning in, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!